Isomers that are position isomers are said to have the same molecular formula too, but they differ in the position of their functional groups. That is to say, they may have the same molecular formula and of course belong to the same homologous series. That is to say, they belong to the same family, but the position of their functional group differs. A good example is, as we can see, these two alkanols, butan 1-ol and butan 2-ol. So positional isomers or position isomers are isomers that have the same molecular formula, but the position of their functional group in the chain changes, hence changing the name of the hydrocarbon itself. Butan 1-ol and butan 2-ol. Let us take a look at what we are talking about. Let's get to understand what that compound is. So we have butan 1-ol and butan 2-ol. They both have a formula C4H9OH. They both have that general molecular formula C4H9OH. Let's look at the first compound. Look at it, OH. Butan 1-ol. Butan 1-ol. When we started the lesson, we said that alkanols end with the name ol. Alkanols ends with the name ol. So looking at this compound, we can see that OH is a functional group. So what it simply implies is we have to start our counting from the right-hand side so that it will give the functional group a low number. And the name of this compound is butan. Butan is supposed to be butane. It ought to be butane because it has 4 carbon atoms. That's butane. But because it has a functional group, which is OH, and we said that OH is alkanol. That is to say, ROH is the other general molecular formula. ROH. So, ROH is a kind of general molecular formula for it. So, since this has 4 carbon atoms and it ought to be butane, because of the presence of OH, that name N, butane, must be changed to the alcoholic name. And to change that, the last E will be replaced by ol. The last E in butane will be replaced by ol. So this becomes butanol. Butanol. So this is butanol. If you don't want to say butanol, we can say butan 1-ol. It is the same thing. Butan 1-ol or butanol. So this is a compound called butanol, and it has 4 carbon atoms, 9 hydrogen atoms, and 1 OH. So as we can see, 4 carbon atoms, 9 hydrogen atoms, and 1 OH is attached to it. So, and that is actually what it is. Now, let's take a look at the fact that we choose to move this OH from where it is now, from carbon 1 where it is. Let's assume we choose to move it somewhere else. If we choose to move that OH maybe to position 2 or position 3, for example, what will become of the name? That is what we are trying to do. So let's try to move that compound. Let's take it this way. So this is C, 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 C. And we have H, 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 H. Now, instead of having OH here, we want to replace the H for this carbon 2. Let's place our numbering still the way it is. 2, 3, 4. So we want to place the OH, instead of placing the OH at the first carbon from the right hand side, let's place our OH here. Let's place the OH here, and then we can complete the hydrogens for the last carbon atom at the right. So we just complete it. So we have swapped the OH that was at carbon 2 with OH that was initially at carbon 1 in the case of butanol. That's butan-1-ol. So having done that, the name of this compound we have formed now is not going to be the same. It's not going to be butanol or butan-1-ol, but it is not going to be butan-2-ol. This is butan-2-ol. Why is it so? It is so because the OH is no longer located at the first carbon atom. Instead, it is at the second carbon atom. So we have to identify the position of the OH. But the number of carbon atoms did not change. It is still 4 carbon atoms. So it is butane. But because it is an alkanol, it must be changed to the ol name. So to change it to the ol name, the E in butane must be changed to ol. And then we have to identify the position of the ol in the chain. And the position of the ol in the chain is at carbon 2. So that is why its name is butan-2-ol. I can hear a student saying, okay, why not we shift it? Let's shift the OH to the third carbon atom. Now, when you shift it to the third carbon, that is to say, if we are to shift the OH to this point, somebody may be saying, now it will no longer be butan-2-ol, it will be butan-3-ol. You are not correct if you are reasoning that way. The thing is, if we are to shift the OH now to the next carbon atom at the left hand side, automatically we are not going to start counting again from the right. Our counting is not going to shift from the left, because the rule says in numbering we have to number from the side that will give the functional group the lowest possible number. You see that? So that is why in this case we still have to maintain counting from the right hand side, because when we count from the right hand side, the OH falls at carbon 2. But if we are to count from the left hand side, it could have fallen at, look at it, 1, 2, 3. Can you see that? And that would be wrong. If we are to count from the left hand side, it means the OH will fall at carbon 3. And that would be very wrong. So that is why we also count from the right hand side. So in every step of organic chemistry, the rules must still apply. The rules for nomenclature apply. The rule for isomerism also apply. So this is an example of a position isomerism. Position isomerism is a kind of isomerism where the position of functional groups are altered. And once they are altered, automatically the name of that compound also must change. So this is an example of position isomerism. Okay, having seen that, let us take a look at another example of a position isomerism. Now let us take a look at this compound. Briefly, we take a look at, this is compound A, and we're going to see compound B. So compound A is that is compound A. So let's look at compound B. Compound B is So, what can we say about compound A and compound B? For compound A, we call that 1-bromo, it's not 11, sorry. This is 1-bromopropane. Propane is 3 carbon atoms. 1-bromopropane. Why? Because we have to start numbering from the left-hand side where the bromine is attached to the carbon atom. Can we see that? That is 1-bromopropane. So, looking at compound B is 2-bromopropane. Can you see? 2-bromopropane. They both have 3 carbon atoms, 7 hydrogen atoms, and 1 bromine atom. They both have 3 carbon atoms, 7 hydrogen atoms, and 1 bromine atom. So, 1-bromopropane and 2-bromopropane are having the same molecular formula, but their structural formula is different because of the position of bromine. Bromine in the first compound is at position 1 of carbon atom, but in the second compound, bromine is at position 2. So this is also another example of position isomers, and it is worthy that we take good note of that. Let us take another example of position isomers so that we may get to understand this clearly. I would like you, dear students, at the end of this organic lesson, you will be so good at naming organic compounds wherever you see them, wherever they see you. So, let us look at this example, and I want to believe that you are actually being fed very well. Let us take a look at the example as we have here. We have this here, and we have that up there. Okay. So, what are the names of these compounds? What are the names of these compounds? Looking at the compound first, looking at these two compounds, they both have the same molecular formula, and their molecular formula is they have 4 carbon atoms and 9 hydrogen atoms with 1 OH. So they have 4 carbon atoms, 9 hydrogen atoms, and 1 OH. That is it. 4 carbon atoms, 9 hydrogen atoms, and 1 OH. That is what they have. So looking at it, this is called 2-methyl propan 1-ol. 2-methyl propan 1-ol. 2-methyl propanol or 2-methyl propan 1-ol. But in this case, this is called 2-methyl propan 2-ol. Can we see that? 2-methyl propan 2-ol, because the OH is attached to carbon 2 in this case, but the OH here is attached to carbon 1. 1, 2, 3. And here is 1, 2, 3. So we can see that it is attached to carbon 2, but in the other compound it is attached to carbon 1. So these are all examples of position isomers. Position isomers, once again, is when the functional group changes location or position. It leads to position isomerism. So away from position isomerism, let us look at the next type of isomers. That is functional isomers. What do we mean by functional isomers? As the name implies, it also has to do with functional group. As the name implies, it has to do with functional group. And what do we mean by that? Functional isomers have the same molecular formula too, but their functional groups this time are different. This does not have to do with the changing of their functional group position. No. That is to say, functional isomers are not isomers whose functional group changes position. No. But in this case, functional isomers are isomers that have the same molecular formula, but they belong to different function. They have different functional groups. Having different functional groups simply implies that they belong to different homologous series. That is to say, a compound A may belong to alkyne and compound B belongs to alkanol, but they have the same molecular formula. Can we see that? So when two compounds have the same molecular formula, for example, they have, let's say, C10H20O5, for example. Two compounds A and B have molecular formula C10H20O5. Take, for example, if they have this same molecular formula, but compound A belongs to aldehyde, while compound B belongs to esters, for example, then they are said to be functional isomers because they both belong to different homologous series, have different functional group, but what they only share in common is molecular formula. That's just what they share in common, molecular formula, probably by coincidence. So if they have the same molecular formula but have different functional groups and hence belong to different homologous series, then they are said to be functional isomers. So let's take a look at the examples as we can see on the screen. There are three compounds, compound 1, 2, 3. They all share the same molecular formula, C3H8O. C3H8O. That is their molecular formula. So, but what about their structural formula? What about their structural formula? Looking at their structural formula, first and foremost, let us take a look at what we have done so far so that you get to understand, as we have said, positional isomers we have seen, chain isomers we have seen. Now we are looking at functional isomers.